All right. So number one, and don't worry about number two, the A values and all that stuff. We're going to talk about that later. All right. But number one, as what the product is of the following reaction sequence. All right. So you have an aldehyde. You have the conditions to make a granular, but then you have some other conditions down here too. So I want you to kind of marinate on that for a second and tell me what you think. All right. So once we get that cis oxyphosphate treated with butyllithium, let me just go ahead and that's an example of Schlosser modification. Remember we talked about this? So it's a way to make trans alkenes with aliphatic ilex. All right, so that's going to convert that. I'm just going to cheat and copy it. Oh, no, I won't. I'll write it out. So that's that. Right, got an empty p. Well, not an empty p orbital, but a carbanion, right, at that site. And then when you add in that allobromide, right, this is an electrophile. Remember, we talked about the fact that with the Schlosser, normally you can add in H plus, but you can also add in other electrophiles. And because of the chirality right there on the cyclohexene ring, that allobromide is going to come from the opposite face. So you're going to end up with this oxyphosphatane that looks like this. Right? And then that is what will undergo that decomposition to give you this trans alkene. I need one more carbon in there. Right? So it's that the other part of that, the second and third steps, those are indicative of the Schlosser modification. Right? That's when you add in a strong base, low temperature, you deprotonate the oxyphosphatane, and then you get that you add in either a proton or another electrophile and invert the stereochemistry at that second carbon. Is that clear? I mean, I know we talked about it, and I don't know if you caught it, but anytime you see the Vidic conditions followed by a strong base, that's normally indicative of doing a Schlosser modification. All right. Let's go back up to the top page, and we're gonna work on number three. It says draw the reaction product resulting from the following arrow pushing diagrams. Include all charges when necessary. All right. Probably should cut these. All right. What do you think for the first one? Can, if you can annotate your screen if possible if you want to draw it in. Anybody who's gonna go first? What brave soul?
Can you repeat that?
All right. Which let me pause this. All right. So obviously this is going to be a new carbon-carbon bond between here and here, and then you'll have a ionic bond between oxygen and sodium, and then a new pi bond here, right? And you're breaking the pi bond between carbon, the two carbons here, right? So that product will look like this, and it's actually a yeah, that's right. Right. This is an example. You're going to see this again. Um, it's called an aldolate, right? It's a intermediate in an aldol addition. Right. What about the next one? What would the product of that arrow pushing mechanism be? Don't trip over each other and answer it now.
I'm not sure.
So what are the arrows indicating? You're going to be forming a carbon hydrogen bond here and a carbon boron bond from that arrow. And then with this hydroboration,
It is okay.
right, it's always sin. They always add to the same face. Right. The reason doing this is because we're gonna see it again when we start talking about triple bonds and how to one way to convert them is to use a borane like thexoborane or catechol borane and then uh, convert it to like a vinyl iodide or vinyl bromide. All right. What about the next one? And if you follow the arrows, then you'll see exactly what's. And we got to. So you're saying there's going to be a double bond here. Let me not do that. Let me do this because I want to show the right geometry. Is that what you mean?
Yes.
And then the CO single bond is broken, right? So now you have this, and that oxygen is negative, and then you got another lone pair here, and that oxygen is positive. I got to get my life together with this pen. Let me just start by using my finger. Life was so much simpler then. All right, good. Let me grab the other half of the problem. Let's see if we can work with that. Again, all of these have a meaning behind them because the last example with the acetal, that's actually a protecting group. That's actually a way to, let me go back to here. And I think we'll do that on Monday. We'll do protecting groups Monday. Right, this is an acetal, what we call an acetal protecting group. It's used for protecting ketones and aldehydes. So ketones, aldehydes, that's how you protect them and keep them from uh, reacting. If they are part of a larger structure, but you don't want them to get touched by any of the reactions that you're doing, then you want to keep them covered up. And that's one way to do it is to put an acetal on them. All right. Let me paste this other half a question down here. All right. So what's happening in that question?
Breaking a double bond. As a reminder, the FAA restricts traveling with small lithium-ion batteries.
So you can see making a new carbon bond there, and then you're also making carbon bond there, right? And then you got a lone pair on nitrogen, and the rest of your everything else is neutral, right? This is an example of one of the reactions we talked about the other day. I forget who had this paper. Might have been it was Morgan, the paper that you did on Monday was a 3+2 cycle addition. All right. What about the next one? Right. You can see the hydrogen is actually leaving, right, as a hydride and attacking the carbonyl. So what do we get from that? We should get this. And then that, right? So these, that's not a positive sign. Right, so that's an example of a how to generate a hydride. And then in the last reaction or the last arrow pushing mechanism, let's see what we got with that. I'm gonna leave that one somebody fill it to either fill it in or walk us through it.